present on the Nash social welfare problem.
Hello everyone, my name is Anari and I'm going to talk about the Nash social welfare maximization problem today. This is a joint work with Shayan Obeskaran, Amin Saberi, and Mohit Singh. So let me jump in by defining what the problem is. So imagine that we have m indivisible items and we want to distribute them to a set of n people. These people have utilities for these items and we're assuming that the utilities are additive. So uij is the utility of person I for item j, and the utility a person receives for a collection of items is just the sum of the uij's in that collection. So the problem of Nash social welfare maximization is we want to partition these items, one partition per player, so as to maximize the product of the geometric mean of the utilities of the people. Okay? So this objective is also known as the proportional fairness in the networking community in TCP routing. It's also known as competitive equilibrium from equal incomes. That name comes from the fact that if these items were divisible, the maximizing allocation would be the one which you would get by giving each person the same amount of money and finding prices that are market clearing. So essentially running a market. So this is in contrast to two other notions. So if you are coming from a utilitarian worldview, if you have that worldview, you would care about efficiency of the allocation and you would try to maybe optimize the average of the utilities of the people. If you really care about fairness, or if you're egalitarian, then you would maybe care about maximizing the minimum utility. So this problem is also known as the Santa Claus problem. So this sits somewhere in between. So this tries to strike a balance between the two. Okay. You can also see that by seeing that this is the L1 average, this is the L negative infinity average, and this is the L0 average of the utilities. Okay. So I will briefly describe what the results are. I will also talk about prior results. Then I will give you a convex programming relaxation of this problem that we use to solve it. Then I'll go over the proof overview. So in the proof overview, we use two concepts. So we relate the problem to permanence in a permanence or the number of matchings in a bipartite graph. And we also use these things called real stable polynomials. Okay, so these are the prior results. So the first result was this m minus n plus 1. So you should always think of m as being much larger than n. M is the number of items. So this is a super constant approximation factor for Nash welfare. Then Cole and Gatzelis improved it or obtained the first constant approximation factor for this problem. Then independently of us, Cole and this list of long authors obtained the 2 approximation factor for this problem. It is also known that this problem is APX hard, so constant is the best thing that you can hope for. What we have obtained is an E approximation algorithm for this problem. So now you might notice that this E is worse than this too. But the techniques are very different. And the hope is that these techniques can be applied more widely to a variety of problems. So for the rest of the talk, instead of the geometric mean, I will focus on the product of the utilities. And instead of an E approximation, I just have to show you an E to the N approximation. Okay. So let me begin with a fractional relaxation that would come to the mind of everybody who will first attempt to solve this problem. Okay. So the typical fractional relaxation is that instead of indivisible items, you would assume that your items are divisible, right? So you would have a variable xij, which is the fraction of item j that you give to player I, right? And then you try to maximize this thing, the product of the utilities. Notice that this is in its current form, it's not a concave program, so you can't necessarily maximize it. But if you put a log behind this, it becomes a concave program. Okay? So you can actually find the optimum of this. But the main problem with this relaxation is that it has infinite integrality gap. Okay? To see that, just think of the example where there is only one valuable item. Okay? So everybody wants this sweater, but nobody wants anything else. Okay? So the optimum integral solution would give this sweater to only one person, and the product of the utilities would be 0, whereas the fractional solution can cheat and divide this item and give one piece to each player. Okay? So what do we do to fix this? We change the convex program in a very algebraic way. So we introduce a set of variables yj. You should think of this as multipliers for the values of the items. So each item has a multiplier for its utilities. The parts in orange are the things that we've added to the previous relaxation. So the utilities of each item get multiplied by yj. And we add the constraint that the product of any set of n yj's should be bigger than 1, should be at least 1. Okay? So there are m of them, there are m yj's. The product of any set of n should be at least 1. Okay? And the rest is the same as the previous relaxation. Okay? Now, it's not clear at all why we can even solve this mathematical program. Okay? But what you can do is you can, again, put a log behind this, and you can do some transformations, and this turns into a concave-convex saddle point problem. So I'm not going to talk about that much. But after some transformations, you can solve this. Okay? So the algorithm we use is we solve this optimization problem. It gives us a set of xij's and a set of yj's. Then the rest is very simple. For each item j, xij's give you a distribution. They sum up to 1. Right? So you give that item j to each person I with probability xij, okay? Independently for all of the items. Okay? So the algorithm is very simple. The analysis is not. And so the main theorem of our paper is that this independent rounding algorithm gets at least e to the negative n times the optimal integral solution. So I'm going to be working with this thing that appears in the objective a lot. So I'm going to name it px of y's. Okay. So this thing is a polynomial in both xij's and yj's, but I'm going to be mostly thinking of it as a polynomial in the yj's. Okay. So that's why x is just a subindex. Okay. Okay. All right. So this is an overview of the steps involved in the proof. Okay, so this is the same polynomial that appeared in the fractional relaxation, and this is the theorem we want to prove. So step 1, I've changed the fractional solution, so it's not even clear now that this is a valid relaxation. Okay, so I have to prove that the fractional optimal solution is at least as much as the integral optimal solution. So step 2 is to show that the expected value of the algorithm is related to this thing that I'm going to call the sum of square-free coefficients of this polynomial. Okay? So if you expand this polynomial in terms of the yj's, you sometimes get a yj squared, sometimes you don't. Okay? So throw away the terms that get a square and sum over the coefficients of the terms that remain. This is saying that the expected value of the algorithm is exactly this. Okay? And then the third step is that this sum of square-free coefficients is at least e to the negative n times the fractional optimal solution. Okay? So I'm going to actually prove this step 1 on this slide. Okay? So think of an integral assignment. An integral assignment never assigns the same item to 2 people. So when you expand this polynomial out, you never get a yj squared. Okay. So this polynomial, when x is an integral assignment, this polynomial is square-free by default. Now, the conditions we had in the fractional solution were exactly that any set of nyj's should have a product of at least 1. Okay? Or in other words, every square-free monomial that you can form with the yj's should be at least 1. So every square-free monomial of the yj's that appear in this product is at least 1, right? Therefore, the sum is exactly the same as if the yj's were all equal to 1, which would be the first relaxation. So for step 2, I'm going to use the notion of the number of matchings in a bipartite graph to show this identity. And step 3 is done using the machinery of real stable polynomials. Okay. So more pictorially, this is my Nashville fair maximization problem. I wrote a fractional relaxation for it. I'm going to first prove that the algorithm that I use to round the fractional relaxation gets a value of the sum of square-free coefficients of that polynomial using a notion of bipartite matchings. Then I'm going to show that this value can be approximated using what appeared in my relaxation. So this step is using the machinery of real stable polynomials, and this step is just based on an intuition on bipartite graphs. So let's do this step first. So there are two things that I want to prove. First, I want to prove that the expectation of my rounding algorithm is the sum of square-free coefficients in my polynomial. The second thing I want to prove, and actually the first thing is proved using the second one, is that the expectation of the algorithm is the sum of weighted matchings in this bipartite graph. Okay, so this is the same graph as before. I've replaced the people and the items with nodes. So on the bottom, I have my people. On the top, I have my items. And the weight of the edge ij is just the fractional value of item j given to I, xij, multiplied by its utility. So I'll prove that the expectation of the algorithm is exactly the sum of the weighted n matchings in this graph. Okay, so this is an unbalanced bipartite graph. One side has n nodes. So for each n matching, I multiply all of the weights and sum over all of the matchings, and this is going to be the expectation of my rounding algorithm. So again, remember that the rounding of my fractional solution was very simple. For each item, I look at all of the people, and I assign it to one of them with probability xij. Okay. So let's introduce these random variables, chi ij, which indicates whether we assigned item j to person I. So the expectation of the algorithm is exactly the expectation of the product of the utilities when you replace the xij's by these chi ij's. Now, if you expand this out, you get terms of this form. Okay? So for each sum, you have to select 1j. I'm going to denote that by the sigma of I. Okay? And you get products of n of these chi ij's. Now, the expected product is going to be in correspondence. So this product is going to be in correspondence with these edges on this bipartite graph. So for each person, I've selected one of the items. Okay. This does not have to be a matching necessarily, because I can select the same item from two different sums. Now, the thing is that if I've selected an item for two different people, this expectation is going to be 0, because both of those variables same thing as before.
We are lucky. Okay, somebody's taking care of it.
Okay. While we're waiting for the projector to warm up again, is there some intuition for the role of these extra yj variables in the mathematical program
Yeah.
as being analogous to Lagrange multipliers for some constraint in the assignment?
Yeah, I've actually thought of that, but if you try to write the dual or the Lagrangian relaxation, it wouldn't be as simple as like saying that somebody comes and like sets or scales all of the uij's by the variables yj. In other words, you can't swap the place of the max and min in the relaxation I've shown you. If that were true, then you could think of the yj's as Lagrangian multipliers. It's not as simple as that.
The light on the projector is now green.
That's green.
Just trying to it's just starting.
Thinks it's freestyle.
Okay, so if I select the same item for two people, this product would be 0 because in my rounding I can't assign this item to two different people. And if none of the items are the same, then because of independence, this product I can replace it by the product of the xij's. Okay. So what I have to do is I have to sum over all matchings in this graph, the product of these values over the edges of the matching. That would be the expectation of my algorithm. Now, remember that the polynomial that I was working with was this. Okay? I'm going to argue that this polynomial is again counting the same thing, the sum over the matchings of the product of the weights. Okay? So if you expand out this product, what you get is there are again some terms that have a yj squared. Those are the terms corresponding to non-matchings. And there are some terms that get no yj squared. Those exactly correspond to a matching. So conclusion, you get that the expectation of my rounding algorithm is the sum of square free coefficients in this polynomial. Even without thinking about the Nash social welfare problem, this polynomial can be still used to capture the number of matchings in a bipartite graph, so it has its own applications. All right, so we've completed this step, the last step. So again, I've shown that the expectation of the algorithm is the sum of square free coefficients of this polynomial. What properties does this polynomial have? It has non-negative coefficients. Okay, so for a fixed x, it has everything is non-negative, so the coefficients are non-negative. It's degree n homogeneous. Okay, it's a product of n linear polynomials, and it is real stable. Okay, so real stability of a polynomial is defined like this. So imagine that you plug in complex numbers into the polynomial. If the imaginary part of the complex numbers that you plug in are all positive, I want my polynomial to not vanish. Okay. This is true for a product of linear polynomials because when I plug in these things into my polynomial, each linear term would be a complex number with positive imaginary part. Okay. Because it's a product of non-vanishing terms, it doesn't vanish. So the actual main theorem that we have proved is that for any polynomial that satisfies the 3 previous properties, so it's degree n homogeneous, it has non-negative coefficients, and it's real stable, the sum of square-free coefficients can be approximated with this thing that appeared in my relaxation. Okay. So I've shown you the hard side of it. Okay, so this is the hard inequality that you have to prove. The inverse inequality without the e to the negative n is also true. Okay, so if you remove the e to the negative n term, the inequality would be reversed. And the reason is very simple. It's because for every square-free monomial that appears in P of y, you've conditioned that monomial to be at least 1. So in P of y, you get at least the sum of the coefficients of those terms. Okay? So the hard part is proving this inequality, that it's also lower bounded by this convex relaxation. So our proof, I'm not going to talk much about it, except to say that it's based, it uses heavily as a result of Gurvitz, which in this language would correspond to the case of m equals n. Okay. So Gurvitz proved, so when m equals n, you essentially only have one constraint here, that the product of your variables should be at least 1, or you can even assume that it's equal to 1 in that case. Then the infimum of P of y subject to that constraint gives you the coefficient of the product of y1 through ym. So our proof heavily uses that. Okay, so that completes step 2. Okay, so conclusions. So we have shown that Nash welfare can be approximately maximized within a factor of e. There are some open directions here. For example, what happens to non-additive valuations? Okay, so if each person has maybe a submodular valuation or other types of valuations, what happens? We have shown some partial results here. We have shown that if people have separable piecewise linear concave, whatever that is, valuations, then you can still get a constant factor approximation. There is another orthogonal direction, which is what happens if you replace the geometric mean with a non-uniform geometric mean. Okay, so geometric mean is you just take the product and then raise it to and then take the nth root. A non-uniform geometric mean would correspond to the case where for each person you also have a weight. Okay, so you raise their utility to that weight and then take the product. This seems to be a really challenging problem that we are not able to handle with our current techniques. We've also shown an independent result, which is that the sum of square-free coefficients of real stable polynomials can be approximated using a convex program. I haven't shown you how it transforms into a convex program, but it can. And the approximation factor is e to the roughly the degree of the polynomial. Okay. So we have recently, with Shayana-Weiskaran, been able to generalize this result to more arbitrary linear combinations of coefficients of these polynomials. So you can read that paper if you want. The big open question is, are there more applications of either this result or similar ones? And with that, I want to say thanks.
I guess I'm curious, on the second bullet of your last slide, the problem of approximating the sum of square-free coefficients of a real stable,
You mean
homogeneous polynomial, but so are there, Is there any hope of getting a p-task analogous to the p-task for counting matchings and perfect matchings in a bipartite graph?
Yeah, that is not ruled out at all. But the challenge is that, so the type of approximation that we have is suitable for optimization problems as well, such as the Nash filter maximization. So if you want your program to be, if you want your approximation to be somehow concave in a set of variables in a certain way, then the APX hardness of, for example, Nash social welfare would prove that it's not possible. But the other direction is, I mean, if you just care about counting problems, if you just care about counting matchings or just approximating this, then there is no hardness result.
Okay.